In movies, you freeze or explode in seconds. In reality, you stay intact and you still have time. But near vacuum starts a countdown, and oxygen loses first. This is not a story about distant stars. It is about minutes you do not actually have. If your suit fails, the question is not, will you die? The question is how fast you lose control. We will follow the first 10 seconds, then the first minute. We will separate myths from measured accidents and tests, and we will end with the only number that matters: how long a rescue still works before damage locks in. Picture the simplest scenario. You are outside a spacecraft and something tears. A seal slips, a hose disconnects, a visor cracks. There is no dramatic sound because sound needs air. The first danger is not cold. The first danger is pressure loss and oxygen loss. Your blood is not suddenly exposed to vacuum. Your lungs are. If you try to hold your breath, you make it worse. Trapped air can expand and injure lung tissue fast. So the best move is the opposite of panic. Exhale and do it immediately. Now the clock starts. With pressure dropping, oxygen stops moving into your blood. You still have oxygen already in circulation for a moment. That is why you do not drop instantly. In documented depressurization incidents, unconsciousness came in roughly 12 to 15 seconds. That number is not a slogan, it is a boundary between action and blackout. Picture the simplest scenario. You are outside a spacecraft and something tears. A seal slips, a hose disconnects, a visor cracks. There is no dramatic sound because sound needs air. The first danger is not cold. The first danger is pressure loss and oxygen loss. Your blood is not suddenly exposed to vacuum. Your lungs are. If you try to hold your breath, you make it worse. Trapped air can expand and injure lung tissue fast. So the best move is the opposite of panic. Exhale and do it immediately. Now the clock starts. With pressure dropping, oxygen stops moving into your blood. You still have oxygen already in circulation for a moment. That is why you do not drop instantly. In documented depressurization incidents, unconsciousness came in roughly 12 to 15 seconds. That number is not a slogan, it is a boundary between action and blackout. Here is what those first seconds feel like, physically. Your chest wants to expand as pressure falls. Air in your mouth and sinuses pushes outward. Moisture on your tongue begins to boil, not burn. Boiling can happen at low pressure, even if cold. It looks like bubbling or foaming, not a Hollywood explosion. Your skin holds you together. You swell, but you do not pop. The bigger threat is inside. Hypoxia is turning your brain offline. At around the 10 to 15 second mark, vision narrows, fine motor control fades, your hands feel slow and wrong. Then you lose consciousness. That is important for one reason. Everything after that becomes automatic failure. You cannot fix a leak while unconscious. You cannot orient yourself. You cannot even keep your airway protected. Now comes the second myth. People think you freeze instantly in space. You do not. Vacuum is a great insulator. Heat does not leave your body quickly without air. You mainly lose heat by radiation, which is slower. So cold is real, but it is not first. The third myth is even worse. People think you die the moment you black out. You do not immediately. If pressure returns quickly, recovery is possible. NASA test reports and decompression studies indicate a rescue window. Roughly 60 to 90 seconds can still allow survival if pressure is restored. Past that, injury risk rises sharply. At exposures beyond about 120 seconds, severe damage becomes more likely. So the real timeline has two clocks. Clock 1 is consciousness. Clock 2 is tissue damage. Now imagine the worst case.
No rescue arrives in that first minute. Your body is unconscious, but still alive. Your heart is still pumping. Your lungs are still moving, unless injured. But the environment keeps doing its work. Low pressure triggers embolism in exposed moisture. It can also drive swelling in tissues. There is a reason flight medicine defined a hard boundary. Above the Armstrong limit, body temperature water can boil. That is around 6.3 kilopascals, far below sea level pressure. Space is far below that. So, you are beyond the line completely. Meanwhile, oxygen starvation continues. Brain cells are extremely sensitive to it. Minutes of severe hypoxia can cause permanent damage. Even if pressure returns later, waking up is not the same. A rescue that restores pressure at 30 seconds is one thing. A rescue at 2 minutes is another thing. Beyond that, the story shifts from survival to salvage. And there is one more trap. If you inhaled right before exposure, your lungs are at risk. Expanding gas can rupture alveoli. That can force air into blood vessels. It can create embolisms, which can kill quickly. That is why hold your breath is deadly advice here. So the climax is not dramatic. It is mechanical. Pressure drops. Oxygen transfer stops. You black out. Damage accumulates invisibly. The longer it goes, the less reversible it becomes.
So how long would you survive without a spacesuit? You would stay conscious for about 10 to 15 seconds. You could still be alive for a short time after that, but the practical rescue window is brutally narrow. If pressure returns within about 60 to 90 seconds, survival is possible. After a couple of minutes, outcomes worsen fast. That is the real horror. Not instant death, but a shrinking door. Science you can hear, dread you can feel. If you had 15 seconds of clarity, what would you do first? This is why spacesuits are pressurized at all. Not to match Earth's full atmosphere, just to keep your fluids stable and oxygen flowing. Even NASA's EVA suits operate at a fraction of sea level pressure. They do it to balance mobility, safety, and breathing needs. Because in space, pressure is life support, and once it is gone, you do not negotiate with it, you race it. If you want the next tape, subscribe. The archive keeps growing.